Let's consider a carbon atom which will have 6 protons in the nucleus, and surrounding the nucleus will be 6 electrons, and they will be uniformly distributed around the nucleus. So we can model the carbon atom as some neutral object. Now let's apply an electric field. The electrons will be pushed down and the protons pulled up by this electric field. So we'll have a distortion of the electron cloud relative to the nucleus. We will model this as a plus Q at the center of mass of the protons and a minus Q at the center of mass of the electrons. And we will define a vector D that points from the minus Q to the plus Q. This configuration is referred to as an electric dipole. We will define the electric dipole moment as the plus charge times the vector pointing from the minus to the plus charge, and the symbol we use for the electric dipole moment is this lowercase script p. So it is a vector, and its units are coulombs times meters. Diamond is an insulator, and it is made up of carbon atoms. Here I've depicted some of the carbon atoms in our diamond structure. Let's imagine taking a proton, which we can accelerate and have it impinge on the diamond so that it penetrates and ends up somewhere inside the diamond like this. There will be a Coulombic attraction between this positive proton and the electrons surrounding the carbon atoms, and there will be a repulsion between this proton and the protons in the nucleus of each carbon atom. This will cause a distortion of the carbon atoms into electric dipoles, and the closer the carbon atom is to the proton, the greater the electric dipole moment of the carbon atom. The result will look something like this. I want to define 2 different types of charges that are illustrated in this figure. Bound charges are charges that are always tied up in an electric dipole, and they're charges that can't really move away from the atom they are associated with. The electron cloud associated with the carbon atom and the nucleus are bound charges that are bound together. In response to an electric field, those carbon atoms can distort some, resulting in electric dipoles. All other charges are free charges. So this proton is a free charge, even though it's embedded in and stuck inside this diamond structure. It's a free charge because it's not tied up in an electric dipole with a corresponding negative charge. It also originally came from a long distance away, whereas bound charges only move in interatomic distance. We will only encounter bound charges inside dielectrics. Dielectric is just another name for an insulator. Let's recall the situation where we had just point charges in free space. We had Gauss's law, which was the integral of the electric flux density field dot ds over a closed surface was the charge enclosed. We also had the electric flux density field was equal to the permittivity of free space times the electric field intensity. So now let's substitute for the electric flux density field the permittivity of free space times the electric field intensity and divide both sides by our permittivity of free space. So here's sort of an alternative expression of Gauss's law for point charges in free space. We have introduced this idea that we have free charge and bound charge inside our dielectric, where the bound charge are these charges tied up in electric dipoles. We are going to retain our definition of the electric field intensity, and that is if you put a test charge at some point in space and measure the force it experiences, dividing by the test charge gives us the electric field intensity. The electric field intensity can be due to both free and bound charges. So our expression for the integral of E dot ds around a closed surface is equal to the total charge enclosed, the free plus the bound charge, divided by the permittivity of free space. Here is where we are going to introduce a distinction. The electric flux density field is going to be restricted to just coming from free charge. Since the electric flux density field is associated with the free charge, we are going to introduce a third electric field to be associated with the bound charge. We are going to multiply this expression by the permittivity of free space and then subtract it from this expression. On the left-hand side, we'll have the integral over a closed surface of d minus epsilon sub 0 times E, and that's going to equal minus the bound charge enclosed. We are going to identify this expression in parentheses as that third field, which is called the polarization, and its symbol is uppercase P. With that identification of this term being the polarization, we have our third Gauss-like law that the integral of P dot ds around a closed surface is equal to minus the bound charge enclosed. So equating these two terms and rewriting them, we see that the electric flux density field is equal to the permittivity of free space times the electric field intensity plus the polarization. So the integral of d dot ds over a closed surface is the free charge enclosed. The integral of P dot ds over a closed surface is minus the bound charge enclosed. And the integral of E dot ds around a closed surface is the total charge enclosed, the free plus bound charge, divided by the permittivity of free space.